Hello and welcome to 3.8 Rates of Change in the Natural and Social Sciences. In this section we're looking at how we could use the derivative to make some applications and solve some application problems. Okay, the first thing we talk about is the average rate of change, which we've discussed in this course earlier. Okay, we talk about delta y and delta x. Okay, this is our old slope formula. So that's for an average rate of change. Okay, you could think of it according to this diagram as the slope of the secant line, okay, the one in blue here. And then if we take its limit as delta x approaches 0 for the derivative, this can be interpreted as the instantaneous rate of change of y with respect to x. Okay, and that would be the slope of the tangent line in pink. Okay, using Leibniz notation, dy dx will be equal to limit as delta x approaches 0. Okay, in physics, s equals some function of t. It is the position function of an object, some particle moving in a straight line. If we do delta s delta t, that's going to be the average velocity over a given time period. V is equal to ds dt, so v is the velocity function. Okay, we take the derivative of the position with respect to time. Okay, and that's the velocity, the rate of change of displacement with respect to time. And then the instantaneous rate of velocity with respect to time is acceleration. So we do dv dt, we get acceleration. Okay, so s equals f of t This is your position. We take the derivative, we get velocity. And then we take the derivative again, we get acceleration. Okay, so let's take a look at an example. The position of a particle is given by the equation. S equals, is a function in terms of t, equals t cubed minus 6t squared plus 9t, where t is measured in seconds and s is measured in meters. Find the velocity at time t. Okay, so we'll go through these questions. First we'll do the velocity. So the velocity function this would be the derivative of the position function. So ds dt, which is equal to the velocity. So which is the derivative, right? Take the derivative of our position function. So just power rule for each term. So we have 3t squared minus 12t plus 9. What is the velocity after 2 seconds? After 4 seconds? Okay, so if we're finding velocity after 2 seconds, that means we're going to do v of 2. Right? So take our velocity function, plug 2 in. Okay, so evaluate this. 2 squared is 4. 3 times 4 is 12. 12 times 2 is 24. 12 minus 24 plus 9, that would give us negative 3. So negative 3 meters per second. Okay, second part to that question, velocity after 4. Okay, so same idea, plug 4 in. Okay, so 4 squared, that's 16. 3 times 16 is 48, minus 12 times 4 is 48, plus 9. 48 minus 48, that's gone. So we have 9 meters per second. Okay, part C, when is the particle at rest? A particle is at rest whenever our velocity is equal to 0. Okay, so for our problem, we would set the velocity function equal to 0. So now when we solve this, we could first factor out 3. We have t squared minus 4t plus 3 equals 0. And then next we would factor the inside out. Okay, so factors of t squared would be t and t. Multiplies to 3, adds up to negative 4. That would be negative 3 and negative 1. Set each factor equal to 0. Okay, so you have t equals 3 and t equals 1. Okay, so that means the particle is at rest after 1 second and after 3 seconds. Okay, next, let's take a look at D. When is the particle moving forward? that is in the positive direction. Okay, so the particle is going to move forward in the positive direction when velocity is greater than 0. Okay, so when we take our velocity function, let's do the factored version. When that's greater than 0. Alright, so let's do a number line test. We know when it's t equal to 1, we get 0. When t equals 3, we get the velocity equal to 0. We want to see what's going on outside of these regions, right? Or within these regions. So to the left of 1 goes to 0 as a test point. So you plug in 0 and 0 into here and here. What do we get? That's negative 1 times negative 3. So that's a positive. So that's good. So between 0 and 1, we're going forward. And between 1 and 3, let's pick a number. Let's say 2. We get 2 minus 1 is 1. 2 minus 3 is negative 1. Positive times negative is negative, so we got negative between 1 and 3. After 3, let's put in 4 as a test point. 4 minus 1, that's 3. 4 minus 3 is 1. Positive times positive. Okay, so we got positive. Okay, so what does this mean? This means our particle is moving in the positive direction between 0 and 1, and it's moving in the negative direction between 1 and 3. Okay, so it's moving backwards, and then it's moving forwards again after 3 seconds. Okay. Alright, let's take a look at our next part. Draw a diagram to represent the motion of the particle. Okay, we'll do that in a second. Yeah, but the idea is we would have forward movement (0 to 1). Then we're going to go backwards movement from 1 to 3. And then forwards movement after 3. But we'll look at the diagram for that in a second. A little more detail. Okay, next. F. Find the total distance traveled by the particle during the first 5 seconds. Okay. Total distance traveled. Okay, so because we know the particle's going backwards and forwards, we have to figure out what is it traveling between 0 and 1. Then what is it going to be traveling between 1 and 3? Okay, these are x values. And then what's going to be traveling, how much is going to be traveling between 3 and 5? Because they want it within the first 5 seconds. Right, during the first 5 seconds. Okay, so to figure out the total distance traveled between 0 seconds and 1 second, let's do f of 1 minus f of 0. We'll take an absolute value. Okay, so we put that into our function. So that would be 4 minus 0. Okay, so 4 meters. Between 1 and 3, so we'll do f of 3 minus f of 1. Okay, so f of 3 we had 0, f of 1 is 4, and then we take absolute value, so we get 4. And then between 3 and 5, we'll do f of 5 minus f of 3. Okay, f of 5 is 20. F of 3 is 0. So 20. Okay, add it all up. 4 plus 4 plus 20. We get a total of 28 meters. Find the acceleration at time t and after 4 seconds. Okay, acceleration is going to be the derivative of the velocity. Okay, so if the velocity is this function, then we have to take the derivative of that, and that'll give us the acceleration. Okay, so let's take the derivative. So we get 2 times 3, that's 6. So 6t minus, and then 12t would just be 12. Okay, so acceleration is 6t minus 12. And then after 4 seconds, so then we would do a of 4, 6 times 4 minus 12. So 24 minus 12, so we get 12 meters. And then the units will be seconds squared. Right, so 12 meters per second squared. Okay, H, graph the position, velocity, and acceleration. Okay, we'll show that in a second. When is the particle speeding up? When is it slowing down? Okay, so let's take a look at the graph then. Okay, the top graph is the earlier graph where we're showing the diagram to represent the motion of the particle. Okay, the bottom graph is the graph of position. Okay, that's the S in pink, velocity in blue, and acceleration in green. Okay, when is the particle speeding up? Well, the particle speeds up when velocity is positive and increasing. So velocity is positive, acceleration is positive. Okay, or it could be velocity is negative and decreasing. So that's when velocity and acceleration are both negative. Okay, so basically the particle speeds up when velocity and acceleration have the same sign. So when we look at the graph, we can see that velocity and acceleration, they're both negative here. Right, they're both negative here, so between 1 and 2. And then they're both positive after 3. Okay, so they're both positive, they're both above here after t equals 3. Okay, so that would be speeding up. The particle slows down when velocity and acceleration have opposite signs. For example, between 0 and 1, velocity and acceleration have opposite signs. And then the same thing between 2 and 3, we have accelerations positive, velocities negative. So again, they'll be slowing down there as well. Okay, let's take a look at another example. Linear density. Okay, a rod or piece of wire is homogeneous, then in linear density is uniform and defined by the mass per unit length. Okay, so we have a formula. Okay, linear density is rho equals mass divided by length and measured in kilograms per meter. Okay, so to get the average density, we would take the difference in mass and divide it by difference in length. That'll be average density. And to get our linear density, we would take delta m divided by delta x. Okay, we take the derivative of mass with respect to x. Okay, and that would give us our linear density. Okay, derivative of mass with respect to length. So if they give us mass formula, m equals f of x, which equals the square root of x, where x is measured in meters and m is measured in kilograms, then the average density of the part of the rod given by x between 1 and 1.2 meters is, so let's figure it out. Average density they want. Okay, so average density would be delta m over delta x, okay, which would be, in this case, f of 1.2 minus f of 1 over 1.2 minus 1. Okay, so if we plug in 1.2 into our function, we're going to get square root of 1.2 minus, plug in 1, square root of 1 is 1, and then 1.2 minus 1 would be just 0.2. Okay, so doing this gives us approximately 0.48 kilograms per meter. Now our density, okay, linear density, at x equals 1 would be, so let's figure that out. We said linear density is dm dx, okay, is rho equals dm over dx, and then we would evaluate at 1, so we would plug in 1. So for the function, if the function is square root of x, which is x to the 1/2, then to get the rho will be the derivative, so we'd have 1/2 x to the negative 1/2, in other words 1 over 2 square root x. And now we plug in 1, so plug in the 1, so we'd have 1 over 2. Okay, which is our 0.50 kilograms per meter. Okay, current is the derivative of charge. Okay, so we have average current. Okay, we call it delta Q over delta T. Okay, so that would give us average current. And then the current at a given time would be dq dt, and that would give us current, right? The rate at which charge flows through a surface. Okay, it's measured in charge per unit time. Often we call it amps, coulombs per second. Okay, but that would be an application using the derivative with electricity. Chemistry. A chemical reaction results in the formation of one or more substances. Okay, we have the concentration of a reactant is the number of moles per liter and is denoted by the square brackets. So we have these A, B, and C are all functions of time t. The average rate of reaction of the product C over a time interval is delta C over delta t. Chemists are more interested in the instantaneous rate of reaction, which is obtained by taking the limit of the average rate of reaction as the time interval approaches zero. Okay, so again, we see similar themes between different topics, different genres. Right? We got the average and we got the instantaneous. Okay, so rate of reaction, dC dt. Since the concentration of the product increases as the reaction proceeds, the derivative will be positive, and so the rate of reaction will be positive. The concentrations of the reactants, however, decrease during the reaction. So to make the rates of reaction A and B positive numbers, we put minus signs in front of the derivatives of dA dt and dB dt. Okay, since A, B each decrease at the same rate that C increases, we have this relationship. Okay, more generally, it turns out that for a reaction of the form we have this relationship. Okay, so there's a chemical example to it. Compressibility. One of the quantities of interest in thermodynamics is compressibility. If a given substance is kept at a constant temperature, then its volume depends on its pressure. We can consider the rate of change of volume with respect to pressure, namely the derivative dV dP. As P increases, V increases. The compressibility is defined by introducing a minus sign and dividing its derivative by volume V. Okay, so isothermal compressibility, beta equals negative 1 over V times dV dP. Thus, B measures how fast per unit volume the volume of a substance decreases as pressure on it increases at a constant temperature. For instance, volume of a sample of air at 25 degrees Celsius was found to be related to the pressure in kilopascals by the equation V equals 5.3 over P. The rate of change of V with respect to P when P equals 50 kilopascals is, so here we would take the derivative because we want a rate of change of V with respect to P. So we're going to do dV dP. So that would be, well, right now it's 5.3 times P to negative 1. We take the derivative of that, that would be negative 5.3 P to negative 2. Okay, so negative 5.3 over P squared. Now they give us P is equal to 50 kilopascals. So plug in the 50 into our P. So negative 5.3 over 2500. okay, which will equal about negative 0.00212 meters cubed per kilopascal. Okay, compressibility. Okay, so this was our formula for a beta that we saw earlier. Negative 1 over V dV dP. And then we would evaluate P equals 50. Okay, so we have 5 point well, it's 1 over V, so that's going to flip V equal to 5.3 over 50. That's going to flip in this case, so that'll be 50 over 5.3. And then we would multiply by dV dP, so that's 0.00212. Okay, multiply it all together. So we get 0.02 meters cubed per kilopascal per meters cubed. Okay, biology, rate of growth of a population. Let n equals a function of time, number of individuals in an animal or plant population at time t. The change in population size between the times t1 and t2 is delta n, which equals f of t2 minus f of t1. So the average rate of growth during a time period is delta n over delta t. So that would give us average rate of growth. And then the instantaneous rate of growth, okay, is obtained from this average rate of growth by letting the time period delta t approach 0. Okay, so basically dn dt. That would be the instantaneous rate of growth. Okay, strictly speaking, this is not quite accurate because the actual graph of a population would be a step function that is discontinuous whenever a birth or death occurs and therefore not differentiable. However, for a large animal or plant population, we can replace the graph by a smoother approximating curve, as in this figure. Okay, so this would be an approximating curve in pink. To be more specific, consider a population of bacteria in a homogeneous nutrient medium. Suppose that by sampling the population at certain intervals, it is determined that the population doubles every hour. If the initial population is n sub 0 and the time t is measured in hours, then in general f of t, okay, it's going to be a doubling formula, 2 to the t power times the original population, initial population. Okay, so original population times 2 to the t power. And if we take the derivative, so let's do the derivative of this. Rate of growth okay, so this is going to follow off of our derivative formula for exponential term. Okay, like if we have a to the x, derivative of a to the x is a to the x times ln of a, right, times natural log of a. So for this problem, the rate of growth for bacteria population, dn dt, this will equal, if we take the derivative here, it'll be, well, n0 is just a constant, so just have the n0 there. And then if it's 2 to the t, we would have 2 to the t, and then times ln, natural log of 2. Okay, so let's say we had an initial population, so say n0 equals 100. Then the rate of growth after 4 hours, so rate of growth after 4 hours would be what? So let's plug into this formula then. So we have dn dt, and then we would plug in t equals 4. So we have 100 times 2 to the 4th times ln 2. 2 to the 4th is 16. 16 times 100, that's 1600 times ln natural log of 2. So that gives us approximately 1,109 bacteria per hour. Okay, blood flow. When we consider blood flow through a blood vessel, such as a vein or artery, we can model the shape of a blood vessel by a cylindrical tube with radius r and length L, as illustrated in this figure. Because of the frictions at the walls of the tube, the velocity v of the blood is greatest along the central axis of the tube and decreases as the distance from r from the axis increases until v becomes 0 at the wall. So it's fastest in the middle, okay, along the axis, and then it decreases as you get towards the walls. Okay, the relationship between v and r is given by the law of laminar flow, discovered by the French physician Jean-Louis Marie Poiseuille in 1840, and this is the formula he came up with. Okay, P is the pressure difference between the ends of the cube. Eta, Greek letter eta, is the viscosity of the blood. Okay, and then we have L, our constants. Okay, average rate of change of the velocity, okay, would be delta V over delta R. If we let delta R approach 0, we obtain the velocity gradient, okay, which is the instantaneous rate of change of velocity with respect to R. So dV dr, that gives us the velocity gradient. Okay, so if we take the derivative of that first equation we showed earlier, we end up with this formula. Okay, that would be the velocity gradient. Okay, so if we have smaller human arteries and we plug in these values, we could get an approximation of the velocity and the velocity gradient. Okay, marginal cost in economics. Suppose C of x is the total cost that a company incurs in producing x units of a certain commodity. The function C is called a cost function. If the number of items produced is increased from x1 to x2, then the additional cost is delta C, and the average rate of change of the cost is delta C divided by delta x. Okay, the limit of this quantity as delta x approaches 0 is the instantaneous rate of change of cost, which is called the marginal cost. Okay, so let's take a look at an example. Suppose a company has estimated that the cost in dollars of producing X items is this, right? Then the marginal cost function is, so we would just take the derivative. So that would be 5 plus 0.02x. The marginal cost at the production level of 500 items is, so now we plug in 500 into our marginal cost formula. So 5 plus 0.02 times 500. And that gives us that that'll be $15 per item. This gives the rate at which costs are increasing with respect to production level. When X equals 500 and predicts the cost of the 501st item. The actual cost of producing the 501st item is, okay, so here we have to figure out what's the cost of 501 items, and then we'll take away the cost of 500 items. Okay, and we see that if we plug in 501 into our formula, we'll have 10,000 plus 5 times 501 plus 0.01 times 501 squared, okay, minus 10,000 plus 5 times 500 plus 0.01 times 500 squared, okay, then we'll end up with $15 and 1 cent. Okay, so notice the $15 per item that we got earlier is actually very close to the number we calculated when we wanted to find out the actual cost of the 501st item. Okay, economists also study marginal demand, marginal revenue, marginal profit, okay, which are the derivatives of demand, revenue, and the profit functions. Okay. So you guys can see we have an idea and we have many different interpretations. Right? We have an average of something, like an average slope, an average cost. Then we have an instantaneous velocity, instantaneous, cost by taking the derivative. Okay, so many different interpretations, many different places where the derivative is used. It's just a matter of working out the math and figuring it out. Any questions on any of this stuff, just reach out to me. Have a good day. Have a good night. We'll see you soon.